Hello, everyone. So last 3 chapters of the semester, right? I know that things have gotten a little bit difficult because we've started getting into reactions. Um, you know, good news is, I guess good news, bad news, it's going to be the same sort of format throughout the rest of the semester as well as into the second semester, where basically we will learn a new functional group, we learn a bunch of reactions for that functional group. So we're going to pick up now with a new functional group, which is alcohols. So first, let's just get into like nomenclature and physical properties and all that good stuff with our introduction to alcohols. Alcohols are easy to spot because, of course, they have that functional group, the hydroxyl group, right? So the OH group. And in terms of nomenclature, this is indicated by the ending "ol," right? So ethanol, that OL ending, is indicative of that alcohol functional group. The chapter is kind of oddly named Alcohols and Phenols. We're not actually going to talk about reactions for phenols or even really how to name substituted phenols until we get to the next semester. But I guess it is important to just introduce what phenol is. And that's this guy here, right? So that's when you have an alcohol group that's directly attached to a benzene ring. And we'll see phenols do have some specific or some interesting acidity properties. We'll get into that in a second. So first of all, how to name these things. So it's kind of similar to our other functional group compounds that we've learned. Again, in here, the color coding of blue indicates any sort of changes that we've had to our normal nomenclature scheme. There is another thing that we want to introduce, though, which is this idea of a priority of functional groups. Okay, so real quick, these are different functional groups, right? So alcohols, that's something with this generic property. Thiols, if you remember, we learned all these functional groups sort of at like the beginning of the semester, but it's been a while since we've talked about them. Thiols are groups that have an SH, so similar to an alcohol, but with sulfur instead of oxygen. Amines have this nitrogen group, and then of course we know our alkenes, those are double bonds, and alkynes are triple bonds. Okay. So it turns out that in organic chemistry, all these functional groups have been sort of ranked and given a priority. So what the heck does that mean? Well, the higher, so first of all, whenever you're going to go and find your parent chain, they should always include all the functional groups. Sometimes that isn't possible. If you have 3 or more functional groups, maybe you can't find a parent chain. We're not going to get into any examples like that. Okay, but it could be that you have 2 functional groups on your parent chain, and that's when priority is really important. The idea behind priority is that the highest priority functional group should get the lowest number. So what do I mean by that? Well, we're not really going to talk about, we'll get to thiols next chapter, and amines, I think we wait until next semester. And then actually this whole prefix business, that'll be important when we get to next chapter, but we can just ignore that for now. But let's actually just look at a compound that has both an alkene and an alkyne functional group, right? So something like this. Oops. Well, so again, the whole idea of priority is that you're going to find which is the higher priority functional group. So in this case, again, we have this alkene group as well as the alkyne group, but the alkene group is the higher priority group. And that means that it's going to be the one that gets the lower number. So we would actually number from this end, 1, 2, 3, 4, 5, 6, 7, as opposed to going the other way. So alcohols, we're going to learn our highest priority group. So we're always going to number such that the alcohol group gets the lowest number. Okay. So again, big differentiation is this "ol" suffix, right? So if we have a 5-carbon alkane, that's pentane. If we have a 5-carbon alcohol, that's a pentanol. And again, just like with our other functional groups, you want to make sure to number or when you're finding your parent chain, it should include that functional group, right? So this compound without any sort of functional groups, we would find just the longest set of contiguous carbons, so it would be an octane. But as soon as we put an alcohol on this carbon here, that now has to be a part of the parent chain. So this changes to a hexanol, and in particular, this would be 1, 2, 3. So this would be 2-propyl 1 hexanol. Okay. And then in terms of numbering, like I said a few slides ago, but nonetheless, something important to remember, you want to number such that that highest priority group, in this case, the alcohol group, gets the lowest number, right? So this numbering scheme on the left would be the correct, because even though we have this double bond over here, that's lower on our priority ranking than alcohols. So we're not going to consider that. We're going to make sure that it's in the parent chain, but we're not going to try to give it the lowest number. Instead, the lowest number will go to the alcohol group. Right, so that's why we start numbering from over here, 1, 2, giving that alcohol 2, as opposed to the other direction, which would have given it a 6. Okay, and then just like we saw before, you got to indicate the position of that functional group using these numbers. So in this case, this is a pentanol or a pentane main chain, 5-carbon main chain, and the alcohol group is at position 3. So you can either write this as 3-pentanol or pentan-3-ol. Okay, and again, it seems kind of weird as to why we would have these two equivalent ways of naming things. But now we're going to see an example where this second one is actually really important. And that's when you have two of these functional groups that are both suffixes, right? So in this case, double bonds would be these ene or ene suffixes. And then we have the alcohols, which is the ol suffix. So if we're going to name something that has both of these functional groups in it, I guess first let's note that we have 1, 2, 3 methyl groups. So this is still 5, 5, 6 trimethyl. But then when we're going to include both of these suffixes, we're going to indicate it where they are in sort of this fashion over here. So this would be hept 6-ene 2-ol. All right, so again, as I said, it's sort of weird why we would ever want to just like put the number in the middle of the name like this, but it's in these exact same situations where you have two suffixes that you need to include. In this case, the ene and the ol. And so this, right, we're indicating the position of the double bond at the 6th carbon, and we're indicating the position of the alcohol group at the 2nd carbon. All right, so that's when you absolutely have to include the number like within the name as opposed to out front. As you would probably expect when we get to cyclic alcohols, again, you want to make sure that that alcohol group always has the lowest number. And since it's in a ring, you can kind of start arbitrarily. You're always going to number such that the alcohol group is positioned at carbon 1. Right, and then you're going to, whether you go clockwise or counterclockwise, would be in order to give whatever the other functional group is that lowest possible number. Notice if you have just cyclopentanol, so just one alcohol group, there isn't that second position there. You don't actually even include the numbers. So this wouldn't even be 1 cyclopentanol because the alcohol group has to be at carbon 1. Similarly, over here, you're indicating the position of the methyl groups, 3,3-dimethyl, but then it's just cyclopentanol because again, it's implied that the alcohol group is at carbon 1. Just some common names. These aren't ones that I would expect you to know on an exam. Like I'm not going to ask you for common names, but it is just good to see because you probably have heard about these. So rubbing alcohol that you get to clean wounds, right? That's isopropyl alcohol. Really the systematic name for that would be 2-propanol. But remember, those iso groups are like little forks. Similarly, butyl alcohol would be, the real name would be 2-methyl-2-propanol. But again, that has like that tert-butyl group, that 4-carbon with many branches. And then benzyl alcohol, notice that this is different from phenol because the alcohol group is located one away from the ring, right? Phenol would be when the alcohol group is directly attached to the ring. Benzyl alcohol is one removed. When it comes to naming diols, so you're going to use the suffix diol, and so diol meaning there's two alcohol groups. You're going to use the suffix diol at the end, so just putting di in front. And then the other kind of weird thing about naming diols is that you don't drop the E from the alkane name. So instead of being like propanediol, it's propane diol, right? With both of those alcohol groups positions being indicated. In this case, how was I numbering? Notice that I went from left or from right to left in order to use the lowest numbers possible for these alcohol groups. But again, this is now hexane diol instead of like hexanediol. And then another sort of common name is this idea of glycols are used to refer to compounds that have multiple or that have two alcohol groups. So ethylene glycol is by far the most famous. It's really important in biochemistry. And that is two carbons, hence the F. And then the glycol is what's indicating that there are the two alcohol groups. Okay, again, just sort of common name stuff. Just like what we saw with our alkyl halides, we can indicate, or I guess like describe these alcohols more by talking about how many carbons the alpha carbon is bound to, right? Alcohol groups can only have one bond. So it's always going to be just bound to one carbon. But then we categorize these as primary. If that alpha carbon is bound to one other carbon, that would be primary. If the alpha carbon is bound to two other carbons, it's secondary. And if it's bound to three other carbons, it's tertiary. Okay, we talked about physical properties of alcohols way back at the beginning of the semester, but let's just remind ourselves, alcohols tend to have very high boiling points relative to, their alkane or even alkyl halide counterparts. Remember, boiling point, melting point, these are good measures of how strongly neighboring molecules are interacting with one another. And alcohols can interact with one another very strongly because they can do so through hydrogen bonding, right? So the OH, or the oxygen in that alcohol group, is a good hydrogen bond acceptor, and the hydrogen in that OH group is a good hydrogen bond donor. All right, so these are polar groups, and they can interact with one another in neighboring molecules really strongly. That means that most alcohols have these kind of like dueling parts of them, right? So they have one half. So if we take something big like this, you have one half that's this big hydrophobic region. It's consistent of just hydrogens and carbons, no polar bonds there at all. And then the other half of the molecule is that very polar hydroxyl group. These words, hydrophobic, water hating, hydrophilic, water loving. These are actually mainly terms that you hear in biochemistry, but nonetheless, hydrophilic is just another way of saying polar, whereas hydrophobic is another way of saying non-polar. And so most alcohols have like dueling halves of the molecule. You have your functional group that's really polar, but then the other half of the molecule is just this carbon hydrogen backbone. So a good rule of thumb is that alcohols with 3 carbons or less will be miscible with water. Alcohols with 4 or more carbons will be, there's a little cutoff zone, like butanol is like slightly soluble. And then you get to like pentanol, hexanol, etc., and those are completely immiscible. We also talked a little bit about the acidity of alcohol groups. So alcohol groups are not terribly acidic, but it's not impossible to remove that hydrogen or deprotonate that alcohol. You just need a relatively strong base. So sodium hydride, another example would be the amide ion would be a good strong base that you could use. And if you did this, what you would generate is what we call these alkoxide ions, or deprotonated alcohols. And we see these alkoxides being used as strong bases a lot in our substitution and elimination chapter, right? So they're good, strong bases. Turns out that you can also accomplish this by taking an alcohol and just mixing it with either solid sodium, potassium, or lithium. Remember, these are atoms that really like to give up their electrons very easily. And so that's a way that you can use to generate your alkoxide ion as well. Okay, and again, these are really useful strong bases, is why you might want to do that. And again, so then we can, if we remember back to why compounds are more acidic or less acidic, it all has to do with the stability of that conjugate base, right? So in terms of our alcohols, they kind of fall over here. You would need something stronger. So for example, the amide ion or this carbanion of sorts in order to actually deprotonate the alcohol. The pKa's are typically between like 15 and 18 for an alcohol. So they're not something that you would think of as being terribly acidic. That proton's not terribly easy to donate, but it can be done with a strong enough base to remove that proton. One of the things that would increase the acidity of an alcohol is resonance. So if we just compare cyclohexanol's pKa to phenol's pKa, we can see that phenol has a much lower pKa. That acidic, or rather that alcohol proton is far more acidic than it is without the conjugation of the benzene ring. And that's just because you can, again, it has everything to do with the stability of the conjugate base, the stability of what's called the phenolate ion, or I guess phenoxide as well, is more stable because it can sort of spread that negative charge around that benzene ring through resonance. Another thing that would increase the acidity of an alcohol is the presence of electron withdrawing halogens. So for example, comparing ethanol to trichloroethanol, you can see that the trichloroethanol has a much lower pKa. Remember, we had our REO. This would be, we went over the resonance. This would be the induction consideration for REO. A was atom, but since we're talking about alcohols all the time, it's going to be an oxygen. And the last thing that differentiates, and this is a much smaller difference in pKa, right? When we were talking about cyclohexanol to phenol, that was a difference of like 8 pKa units. When we're comparing ethanol with tert-butanol, that's only a difference of 2 pKa units. But the difference here, it's harder to remove that proton from tert-butanol. So why is that? This has everything to do with solvation effects. Again, what makes something more acidic is the stability of that conjugate base. Well, with tert-butanol, because it's so big and bulky, the solvent molecules can't get around and solvate or protect, stabilize that negative charge in the alkoxide ion, versus ethanol, which is much smaller. And so that oxygen is much more accessible and solvent can get there and sort of stabilize that alkoxide ion in the case of the smaller alcohols.